Hi guys, this is Dr. Edwards once again. So I want to continue with my second video here on the statistics in quantum mechanics, the fundamental statistics that are invariably used for every problem. Back to the infinite square well. So what we have is a particle trapped in this infinite well. It cannot get out. It cannot be beyond x equals a, and it cannot be here in the negative range either. This is the origin. So that means that the potential energy of the particle is zero in here. There is no force on the particle. There is no um, potential on the particle either. And the potential goes to infinity at x equals a and at x equals to 0. Therefore, the particle cannot escape beyond this point. Okay, we've said that before. Now, the wave function that we get for this, and you've already gone through that, you've seen how to get the wave function and the energy. So the particle then is manifested in discrete energies from n equals 1 as far as you want to go. 1, 2, 3, 4, 5, 10, 100, 1,000, etc. And the energies is given by, in this case, n squared, pi squared, h bar squared over 2m_a squared, where m is the mass of the particle. A is known, lowercase a is known as the dimension of the well. And of course, h bar is Planck's constant, the reduced Planck's constant, h bar over 2. So therefore, the energy here can come out in joules if you calculate it. I tend to like my students to convert joules to EVs in this course. The wave function then is normalized by integrating the unnormalized wave function from 0 to a of a squared sine squared of kx, and you get then that a itself is the square root of 2 over a. So this is a normalized wave function here. And the ground state is n equals to 1. Okay, let me now go here. There's one other thing I want to say in passing. Since all these functions generated from solving the Schrodinger equation, they are known together as orthogonal functions. These are mutually determined functions. There's something interesting about orthogonal function. It turns out if you integrate any one of them against the other, you will get a 0 all the time. But if you integrate any one of them with itself, the complex conjugate of itself, you will not get 0. So these functions are called mutually orthogonal. And the author goes through here and show you that if m and n are equal here, you get from the Kronecker delta that the integral is equal to 1. If m and n are not equal from the Kronecker delta, it's equal to 0. Now, what I've done, I've taken the liberty now of calculating the statistics that you want to get for the ground state of the infinite square well. So I have written here, determine the statistics, put an S on that, of the ground state of the infinite square well, and show that delta x times delta piece of x is greater than h bar over 2. This is always true, and I want you to validate that that is the case for this problem. Where here sigma of x is the deviation from the means along the x-axis, and sigma piece of x is the deviation from the means along piece of x. So there is some competition between the particle being at x and the particle leaving from being at x, meaning that you can't know the position of a particle exactly and know its momentum exactly at that same time. That's not possible in quantum mechanics. And the way that expressed it that's not possible is to show, and we'll do that, that the uncertainty principle holds, okay? All right, so the first thing I'm going to do is repeat normalizing the wave function. And what you do, you set up the integral, you say from minus infinity to positive infinity. But since the wave function is zero everywhere outside of this range, the integrand is going to be zero from negative infinity up to zero. And from a to positive infinity is zero, so I don't have to include it. So it's only going to be something other than zero from zero to lowercase a, which is the distance, the width of the well. All right, you come here, you get this integral here to be integrated. I don't mind. In fact, I encourage you to use the table of integrals. So from the table of integrals, you find that the integral of the sine square of a constant x dx, the argument of the sine is squared is bx, is equal to x over 2 minus sine of 2bx over 4b. So use this from the math table. You can find that integral there. And now when you make the appropriate substitution, put in the lower limit, the upper limit, and you find that a, just as we've already indicated, capital A now is known as the square root of 2 over lowercase a. That means capital A is now known. And whereas it was not known previously, now you use this capital A in the expression. So the normalized wave function is the square root of 2 over lowercase a, the sine of n pi x over a. Notice the units here of psi. A has units of meters, therefore psi has the units of square meter, the square root of a meter. That's not measurable. So the psi itself is not a measurable quantity in quantum mechanics. But what is measurable, as you will find later, is psi star times psi, which is the magnitude of the wave function squared. So it turns out, young people, the greatest task in solving the Schrödinger equation, yes, is to get the wave function, but the wave function by itself doesn't tell you much. It is the wave function, the complex conjugate of the wave function, times the wave function. That is measurable. That actually means something, okay? All right, so now let's get on with the 7 statistical quantities that I would want you to calculate for the ground state. Now the ground state is when n equals 0, so I set n equals, I'm sorry, in this case n equals 1, so I set n equals 1 here, and there we have it then. The square root of 2 over a sine of pi x over a. That's the ground state wave function. Now find the statistics in this case. 1, 2, 3, 4, 5, 6, and 7 quantities here. 1, 2, 3, 4, 5, 6, 7. This is just a product. So once you get sigma x, and once you get sigma p sub x, you multiply the two together. And that's what you get. Also, be cognizant of different textbooks use different symbolism for these same quantities. In my book that I give you problems from sometimes, what is it called? Quantum Mechanics Demystified. This quantity is called delta x, and that's called delta px. So you just have to be aware that different authors are going to use different symbols. Okay. So I get on here now, and so the first thing is to set up is to find the expectation value of x. X has to be sandwiched in between the two wave functions. I'm going to look for this when I test you on this. So although it doesn't matter when it's x, it profoundly matters when it's p sub x. Therefore, I want you to get in the habit from the beginning of putting the operator in between psi star and psi. So, okay, I put in psi star. In this problem, it happens to be that psi star and psi are the same because they both are real. And then x in the middle, and then psi dx dx. Now you have to set up the integrand before you can calculate this standard Riemann integral. And so this is the integrand although the symbolism is a little strange, this is still lowercase x, same as it is there. It's just my penmanship. All right, so it's 2 over a. Now 2 over a is measurable because a is unit of meters, and then if all of this becomes inverse meters, then it's measurable. But the square root of 2 over a has no physical meaning. Now, okay, so in order to perform this integral, I go to my math table once again, and there it is. The integral of x sine square bx is equal to this quantity here. So I put in the requisite number of quantities here. I make the appropriate substitution, blah, 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 and blah, blah, blah. And I get that the expectation value of x is a over 2. In the analysis, that makes sense. Halfway between the two extremes, 0 and a, the particle got just as much likelihood of being on the left side of a over 2 as it is on the right side of a over 2 statistically. Therefore, you will find that the expectation value then, in this case, would be a over 2. Similarly, now go on. I find the expectation value of x squared, and it's this expression. I go to the math table right here, and I need to get it in the format so I can use the math table. So I let v equal to pi over a x, dv is equal to pi over a dx, make the substitution back here, and I get the expression in this form so I can use this. Of course, there's some constants that's going to come out front. And I make the substitution, and I go through the calculation, and I get the expectation value of x squared as being a squared over 3. That makes sense. The expectation value of x squared has to be in units of meters squared, because this is x is distance in this problem. Therefore, it has to be meters squared. And so the units analysis mean that is correct. Now I do a sum, and I go on and calculate the uncertainty, and the uncertainty is here, and I get the uncertainty along the x-axis is a over 2 square root of 3. I now come here, and I need to find the uncertainty in px. I remind myself what px is. It's negative I, the imaginary I, h bar the partial with respect to x. The uncertainty in px squared that I'm going to need later, I go on and calculate that too as a negative h bar squared, the second partial with respect to x. So here then, go now, put it in there. You have to put px sandwich in between psi star and psi. I've done that here. Then you have to take the partial of this quantity in order to configure the integrand. So I show you right here. This is to take the partial. I've taken it there. I substitute it back in, and then I integrate. I use a table because I got the integral from 0 to a of sine pi over a, cosine pi over a, and I need to integrate that. I go to my table, and I get this expression, and plug that in, and I get what I expect, that the expectation value of p sub x is equal to 0. The momentum to the left, the momentum of a particle moving to the left is just as likely as one moving to the right. So therefore, I expect that the momentum would be 0 for this problem, that the expectation value of the momentum would be 0. I go and calculate p sub x. I put it in here, turn the crank, and I get it. I make the substitution here as well. I get p sub x, the uncertainty in p sub x squared, as h bar power a. I produce the product of the two. Now notice that it's h bar over 2. So you always want something times h bar over 2. I put it in here, single out h bar over 2, and I get 1.73 h bar over 2, which is greater than h bar over 2. That's what I wanted you to get at, young people. So this is an illustration of the statistic that you would do in every problem that I give you, okay? Have a good day.